Hello, my name is Zhi Fu Gao from Xinjiang Astronomy Observatory, CSA, China, and Dr. Hao Shan is my colleague. My presentation is titled The Electrical Conductivity, Magnetic Parameter, Plastic Flow and Toroidal Magnetic Field Decay in Magnetars. Magnetars are kind of pulsars powered by mainly super high magnetic fields. They are popular sources with many unsolved issues in themselves, but also linked to various high-energy phenomena such as OPOs, giant flares, fast radio bursts, and superluminous supernovae. In this talk, we firstly review the breaking index of magnetars, the eigenequation of ohmic dissipation of toroidal magnetic fields, the crustal electrical conductivity, and the magnetization parameter. Then investigate the temperature-dependent shear rates in the crust of magnetars. My presentation includes the following 6 parts. As we know, magnetars are neutron stars powered by magnetic field energy. Now there are certain magnetar candidates, which are classified as anomalous X-ray pulsars and soft gamma ray repeaters. Compared with common radio pulsars, magnetars universally have longer spin periods, higher period derivatives, and higher surface dipole magnetic fields. Their persistent soft X-ray luminosity, or LX, are higher than rotational energy loss rates. Especially Lx can be higher than 10 to 37 erg per second in magnetars burst and higher than 42 erg per second in its giant flare. This is the P dot diagram of pulsar family. Magnetars are located in the upper right, while the radio pulsars are clustered in the middle and the millisecond pulsars distribute in the lower left of the diagram. A pulsar's secular spin down is mainly caused by its rotational energy losses. A pulsar spin down in the form of power law for a long time, and the power law exponent is called the breaking index. When the magnetodipole radiation, or MDR, solely causes the pulsar to spin down, the breaking index is predicted to be n equals 3. Up to date, only 9 of the 3,000 known pulsars have reliably measured breaking indices, all of which deviated from 3, demonstrating that the spin-down mechanism is not pure MDR. Because of the lack of long-term pulsed emission in quiescence and the strong timing noise, it is impossible to directly measure the breaking index N of a magnetar. Based on the estimated ages of their potentially associated supernova remnants, or SNRs, we estimate the values of mean breaking indices of 8 magnetars with SNRs. From equation 5, the breaking index of magnetar with SNR is determined by 3 observation quantities: spin period, its derivative, and its SNR age. A varying crustal magnetic field yields the breaking indices. From equation 6, a decreasing surface dipole magnetic field, BD, results in a decaying dipole breaking torque, and then the effective breaking index increases to a high value of n larger than 3. In order to reconcile the measured high breaking index for 3 magnetars with their surface field decaying rates, we give an analytical solution to the Hall induction equation describing the evolution of crust magnetic field. This table shows the constrained values of mean breaking indices for 8 magnetars. We found that the 5 magnetars have smaller mean breaking indices of n smaller than 3, and we interpret them within a combination of magneto-dipole radiation and wind-aided breaking. The larger mean breaking indices of n larger than 3 for the other three magnetars are attributed to the decay of external breaking torque, which might be caused by magnetic field decay. In order to account for the high breaking index of cluster J 1640 to 4631, we proposed a coupled model of magnetodipole radiation and dipole magnetic field decay, combining with APR equation of state. This illustrates the previous study on neutron star magnetic field decay. The magnetic fields were universally assumed to exponential in a flat spacetime, and there was no eigenvalue equation for toroidal magnetic field in general relativity. However, there are two factors that slow down the magnetic field decay, namely gravitational redshift and the intrinsic curved geometry of the space section. The inclusion of GRF effects raises the time-space of magnetic field decay, but keep on the same order of magnitude as in a flat spacetime. Here, the magnetic field is composed of the pallidal and toroidal parts, and described in three directions, r, theta, and phi, in spherical coordinates. For the sake of simplicity, we only consider dipole magnetic field corresponding to L equals 1 and M equals 0. The magnetic field is confined in the crust in force-free model, in short, the FF model, through the adoption of the Ronda polynomial, spherical Basel function, Maxwell's equations in a covariant form, and tensor analysis. We deduce an eigenvalue equation of toroidal field in a curved space. In order to calculate the decay rate of toroidal magnetic field, we must investigate the crust electrical conductivity and combine with the EOS and the magnetic field configuration. The bottom diagram denoted the three normalized magnetic field components of crustal field of a neutron star in the FF model. In this table, we list the persistent timing, ages, and emission characteristics for 22 magnetar candidates, with observed soft X-ray flux from McGill magnetar website. Equation 1 is the expression of the soft X-ray luminosity, or Lx, and equation 2 is the expression of the rotational energy loss rate, or LROT. By considering the general relativity effect, we calculated the toroidal magnetic field decay rates and investigated the Lx and the LROT relationship of the 22 magnetars with soft X-ray luminosities. It is found that for magnetars with Lx less than LROT, their observed soft X-ray emissions may come from the rotational energy loss rate, or from magnetosphere flow, and or from practical wind heating, while for magnetars with Lx larger than LROT, the ohmic decay for crustal toroidal magnetic fields can provide their observed isotropic soft X-ray luminosities and maintain high thermal temperatures. This figure shows how drift can not only enhance the ohmic decay but also result in the anisotropy of surface thermal temperatures for magnetars. The contributions to the crust electrical conductivity come from two parts, the electron-phonon scattering and the electron impurity scattering. The crustal conductivity depends strongly on temperature, T, and the density, and the impurity concentration, Q. In previous study, there was little consideration on the effect of super-high magnetic field on the conductivity. Recently, we have performed a detailed investigation on the crustal electrical conductivity and the magnetization parameter. The magnetization parameter is an important quantity related to magnetic field evolution and the thermal evolution of a neutron star, and is defined as the ratio of the ohmic timescale to the high drift timescale. We chose two fiducial dipole magnetic field of 10 to 13 G and 10 to 14 G, 4 different temperatures, T, and 2 different impurity concentration parameters. We have adopted a unified equation of state for cold non-accreting neutron stars with the Hartree-Fock-Bogliub method. In Table 1, we list the principal values of computed equilibrium proton number ZeQ in the inner crust below proton drip for functionals BSK22, BSK24, BSK25, and BSK26 by implementing realistic conductivity profiles provided by Potakin-Pons page into the code and combining with the EOS. We calculate the inner crustal conductivity. This figure shows our numerical results on sigma, omega, and tau in two fiducial magnetic fields. The solid line and the dot dashed line are for sigma, omega, and tau respectively. From the above simulations, it is found that the conductivity increases slightly with the increase of the magnetic field. The enhanced magnetic field has a small effect on the matter in the low-density regions of the crust, and almost has no influence on the matter in the high-density regions. In particular, the low-density regions, the relative increase of rate of the conductivity is less than 5%, and in the high-density regions, the relative increase rate is less than 10 to the power of -3, so the effective magnetic field on sigma, omega, and tau can be ignored. The neutron star's crustal conductivity varies by 3 to 4 orders of magnitude. A high impurity content could lead to even faster dissipation. By comparing subfigures A, B, and C, and D, E, and F, we don't find significant differences in simulations with B equals 1 times to 10 to the power of 13 gas, and B equals 1 times to 10 the power of 14 gas. Here, equation 1 is the general expression of magnetization parameter for young pulsars. Then we apply it to the high breaking index pulsar PSRG1640. We obtain the breaking index as a function of time and initial spin period, initial dipole magnetic field strengths, and the two field decay timescales. By using verified transition state theory and quantum plasticity theory, we calculate the temperature-dependent shear rates as well as temperature-dependent viscosity, considering magnetically driven plastic flows in the neutron star like magnetars. The figure shows the relations between applied shear rates and the strain rate for a solid material, such as a neutron star's crust. We presumed a neutron star crust responds in an elastic, reversible manner to stresses below certain yield value and plastically above it. To construct a useful mathematical formulation, we shall describe the mechanism of slow plastic flow together with a generously boundary condition, using the simplest configuration where one characteristically tiny element in the crust of neutron stars is approximately a slab configuration. The left equation implies a magnetic field with an unbalanced radial component includes an animaso-plastic slip flow in x direction, whose velocity depends on how much one exceeds the elastic part. This also implies that field evolution along the x direction flow provides an ever-increasing twist to the corona. More realistically, this twist could be relieved slowly through viscoplastic dissipation, or suddenly in a corona flare events. The right diagram shows the temperature-dependent shear rate in the crust. In these two PowerPoints, we show our recent works on magnetars, radio pulsars, and GR. Interested colleagues can read them. Welcome to comment our papers in your future works. We have reviewed our recent works on magnetars, breaking indices, crustal conductivity, magnetization parameter, magnetic field evolution, and temperature-dependent plastic flows. It seems to us that a deeper X-ray observation together with a detailed study of future activity periods of magnetars, including simultaneous X-ray optical monitoring, could not only verify our present results but also shed light onto its detailed nature and discern whether the remote source is an ultra-compact low-mass X-ray binary or an isolated neutron star, displaying a new manifestation of magnetar activity. That's all. Thank you very much.